I think we're ready to get started on this last session. So we never got to the offshore features of OpenFAST. We'll talk a bit about that. And then I think the last sections are, understanding the source code a bit for those who want to get to that level. I think Emmanuel kind of talked about getting help, and we have a little bit on that. But and then I think the last section is mostly just summarizing, like, if you're a bit familiar with OpenFAST, I've already sort of mentioned things coming out in 4.0 and 5.0. Talk a bit about some of the things coming down the pipeline, and then we'll leave it at that. I do in the tiny URL link where you download all the files. I also put an evaluation form for the workshop. Very informal, but if you want to provide feedback, I'd love for you to just fill that out. You can just email Emmanuel and I. We can collect those things. So no formal request there, but yeah, if you want to give us feedback, what do you like, what you don't like on the workshop, what do you want better next time? If you want different focuses of something, we'd love to hear what that is. Okay, offshore capability. So again, we can do fixed or floating systems. So again, I think for those of you who've used OpenFAST before, HydroDyn probably. What we did with 4.0 is we extracted all just like inflow wind is separate from aerodyn, although you always use them together. We did the same thing with SeaState. SeaState's been extracted out of HydroDyn as now its own thing, but it basically acts like inflow wind for the wind side. Different options here. So you can do regular or irregular waves. So regular is periodic. You got stochastic waves based on the spectrum. You also do white noise waves, basically a constant energy spectrum over a given frequency range. For irregular, it's basically John swap spectrum approach. Let's see, we've introduced recently constrained new wave capability that's coming in 4.0 as well. What that allows you to do is you can run the irregular SeaState shown there, say with HS of 3 meters or something, and I want to make sure my 50-year extreme wave shows up in that SeaState. So the constrained wave theory allows us to do that. It uses the same characteristic irregular SeaState, but it basically embeds this extreme wave built up, and it follows sort of the physical process where normally what happens is you get some waves that sort of get phase aligned and boom, 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 it builds up, and so you see it. And so basically this constrained wave allows you to make sure that big wave shows up at the time you want, at the location you want in the wind farm. So that's quite a powerful feature. Otherwise, for irregular waves, you got both first and second order theory combined. So first order, that's airy. Second order, we use the Sharma and Dean approach. You can kind of see the effect there in the plot in the middle, where I show the first order in red. The second order component, you see it's small. There's two main things there. There's like a high frequency part, that's the sum frequency term, and then there's this sort of low frequency meandering. That's the difference frequency term. And in the end, when you turn on second order, you basically sum that effect. And really, what it makes is the peaks get a little bit peakier, the troughs get a little bit shallower, and gives you that excitation sort of outside the main frequency range. Just like inflow wind, everything's now available through pointers, and so you don't really see inputs and outputs like that on the SeaState side. Instead, HydroDyn is basically calling SeaState directly to get this data. A couple other things about SeaState. You can do directional spreading. So this is showing, I think actually this is an irregular SeaState with directional spreading, where I embed a constrained new wave in it. So at a given XY point, I say I want that big wave to show up, and it builds it up, and you'll see a big wave come through. So that's definitely in there. The only limitation we have right now for directional spreading is that it has to be basically a product of frequency domain spectra and a directional spreading function. You can't do a full, every omega has a range of betas. Like it has to be a product like that. Just because we shortcut the FFT instead of a big, like in second order, it would be it'd be a 4-dimensional FFT. We only do a 2-dimensional FFT to make that practical. Also in 4.0 now, we've introduced the idea of a full wave grid. Before, it would only define the wave kinematics at the nodes that it needed. In 4.0 now, redefine a full domain of fluid. And so at every point in that grid, you know, the whole free surface gets discretized and you get wave elevations at all its points. Every point in the domain XYZ, you get wave kinematics there. And then basically now in 4.0, when you're on OpenFAST, you can say, you know, do I want to use local instantaneous position as my turbines floats in there? You can use that or not. Basically, you can use the fixed position or you can use the time varying position. And that gets you some second order effects through that motion. Currents are very simple. It's these simple IEC steady current models. HydroDyn, of course, is taking that information now and computing the hydrodynamic loads on the structure. And really, HydroDyn has this, we call it a hybrid model. You can either use strip theory, which is like Morrison's equation. You can use potential flow theory, or you can use some hybrid combination. The plot there in the middle kind of shows the relative importance of hydrodynamic load. So if it's usually large volume bodies, the radiation diffraction are quite important. All potential flow basically dominated, and so that's when you'd use potential flow. If you're talking about very thin members like the pontoons of a semi, or the members of this jacket here, that's where the viscous effects become important in your structure, and that's when you would use strip theory. But often models use a combination then of both. So for our strip theory formulation, again, you define the joints, you define the members, you define the coefficients, added mass, and dynamic pressure coefficients of the body. Also a buoyancy scaling factor there as well. So in addition to like Morrison formulation, we also have buoyancy in there. So it's an analytical buoyancy calculation. Recently in 4.0, we've also added a Mikumi-Fuchs diffraction correction. So if you have a large volume strip theory member, this is a good way of sort of shortcutting the potential flow solution. It really only works for vertical cylinders, but it's a nice option in strip theory. Again, you can do multiple interconnected members like the jacket here. And again, in 4.0 now we've added the interpolation based on displaced position, if you want to have that sort of nonlinear effect in there. And then strip theory is also where it allows you to basically build in stretching theories. So normally you talk about linear theory gets you like up to the mean sea level, and actually in the wave crests or troughs, you want to basically stretch the kinematics up or down. And we have options in that built in HydroDyn to support that. For the potential flow solution, this is for the large volume members. So that figure on the top kind of shows how you would normally do this. Like there's a typical the OC4 deep sea wind semi-submersible. You say, well, I have very thin members, all those pontoons and braces, and I'll say strip theory with that's sufficient. But then those big volume structures, the big offset columns, the heat plate there, that's like, well, radiation diffraction is quite important for that. And so I do potential flow on that. And that's how you basically partition those models out. And so the potential flow solution gives you radiation of the wave. So the structure can push waves and let them radiate away. It can diffract the waves. The wave coming in will be, the shape of the wave will be impacted by the body. Of course, it has buoyancy as well. The HydroDyn formulation allows you to do as many bodies as you want. So like in this semi, maybe you say, well, there's maybe 4 main potential flow bodies there, the middle column and 3 offset columns, and you can have them separate bodies, or you can have it one body. You can also take a given column and say, I want to partition it into multiple bodies. And that's really useful if you want to do the underlying model as a hydroelastic model. So if you want, beam elements, that whole thing, and do hydroelasticity, that's supported, but you have to basically partition the model into multiple bodies. Because otherwise, the potential flow basically just gives you the 6 component force, 3 forces, 3 moments on that body. It doesn't distribute it for you. Let's see. Just like SeaState, this potential flow model supports both linear and second order. So linear, of course, is the REOs effectively get input. Second order, that's like inputting the full quadratic transfer functions. That works in there. Second order, you can do full QTF or you can do Newman's approximation. Let's see another thing there. Normally for the radiation, you're talking about a convolution integral for that memory effect. You can also do a state space form of that, which is really useful if you want to linearize the effect of hydrodynamics and say what's the linear effect of radiation in my model. You can generate that in the model, and then use that linearization. And again, displacement effects and back to displacement on the wave diffraction is in there now in 4.0. All I have on hydrodynamics for substructure, structural dynamics. I think Emmanuel talked about this briefly, but SubDyn is our linear frame finite element model for the substructure. So usually we say, the top of SubDyn is the bottom of ElastiDyn. That's that 6-DOF interface joint. And everything below that gets handled through SubDyn. Because this substructure tends to be a fairly, strong, beefy, maybe not beefy, but strong, that has modes to it, but they tend to be fairly high frequency. And displacements tend to be quite small. We think for this kind of formulation, a linear finite element model for the beam model is sufficient. And so SubDyn is a fully linear model there. It's beam elements. You can have pre-tension cable elements as well. You can connect the beams together through cantilever, pin, universal, or ball type joints, or you can also place rigid links in the model. But because it's fully basically a linear frame finite element model, we do this Craig-Bampton system reduction, as Emmanuel was saying. And what that means is basically we take that finite element model and we reduce it down to these 6 Gaussian modes that connect to the interface joint of ElastiDyn. And then the rest of the modes are basically these constrained modes of the system. This is showing 4 of the modes there for the deep sea wind semi. And these are basically showing the elastic modes of that structure. And you can basically say, so if you're a finite element model like this semi or that tripod may have 1,000 degrees of freedom in it, you can say, well, how many of those modes? You always get 6 Gaussian modes. Those are what connect to ElastiDyn. But then for the rest of the 994 modes, you can say, well, this many are Craig-Bampton modes, and for that, I'll do full dynamics of them, meaning I have a mass, I have a stiffness. But the rest of the modes, maybe you only want 10 dynamic modes. So now we're down to, what is it, 984 modes left. The rest of those I could treat as static modes. Just have the stiffness. Don't worry about inertia, and that's really good to get, needed to get basically, if it's a statically determinate structure, it allows you to get all that flexibility in there without tracking all the dynamics of all those modes. It's a pretty powerful feature. Allows you to do, again, big models with lots of modes, but limited computational expense. If you use SubDyn for floating systems, what that does is effectively the Gaussian modes, your 6 Gaussian modes are basically the rigid body modes of the substructure, and they follow this basically floating reference frames. Whatever ElastiDyn does, they follow along. And then the Craig-Bampton modes are like the internal elastic modes relative to that frame. And again, as of 4.0, that now supports full large motion. So roll, pitch, yaw are all large rotations. For moorings, we have MoorDyn, and if you know things like OrcaFlex for moorings, basically MoorDyn is our version of OrcaFlex. It's lumped mass dynamics. So you discretize a mooring line as a bunch of series of rigid bodies connected by springs and dampers. Can do catenaries or taut lines, full nonlinear geometric restoring. The elasticity can be either linear, like linear springs. A couple versions ago, we also introduced viscoelastic elements, which are quite useful. That allows you to have like a dynamic stiffness that's different than the quasi-static stiffness. So that's pretty powerful. You can do with or without bending stiffness. So the bending stiffness is really useful for dynamic power cables. Usually not very important for catenary, but that term you can turn on or off. You can also put, nonlinear spring elements in there. For example, have some sort of, discrete spring between your mooring line and your fair lead. That's useful for that. Usually there to sort of truncate tension. Let's see. Yeah, added mass and drag are in there. The apparent weight of the lines are there. And then, currently, right now, it's a little unfortunate where if you want wave excitation of the mooring lines, you sort of have to define that separately. Coming in 5.0, we are introducing coupling to SeaState so that MoorDyn can access what the rest of OpenFAST does. So that's coming up in 5.0. Pump weights buoyancy, yes. Line failures is also introduced now in 4.0, meaning at any point in time, you can basically say, well, I have a tension threshold, or a given time, I'd say that line snaps, it's gone. And then you can let the system drift away. Big other part of MoorDyn is dealing with seabed bathymetry and friction. So that's really our sort of workhorse mooring model. If you just want basic quasi-static moorings, that's what's in MAP++. To basically just solve the catenary equations. Not useful for, you know, it's okay for dynamics, but doesn't allow you to get great line tension out of it. Final thing I want to say when we talk about offshore simulations and OpenFAST is that we're throwing wind at the structure, we're throwing waves at the structure, but there really is no direct interaction between them. So the phasing is not really aligned. So the waves aren't generating wind and the wind's not driving the waves. So normally what you do is you take, say, distribution of your, say at a given wind speed, I know my wave condition would be this. That's what goes input into OpenFAST. For given HS, or for a given wind speed, you choose your HS, you choose your TP. That's what goes in the model. So the wind speed will go into your profile, your spectrum of coherence to generate wind. The wave HS, the TP will go into the wave spectrum that will be used to generate the wave. But the time series is effectively completely phase independent. So there's no correlation. So that is a limitation. We do have some high fidelity modeling projects going on now to figure out how much of a limitation this really is. As the waves are propagating, are they pushing wind up? How would that impact the rotor? So I don't know the answer, how important that is. I'm hoping to find out in the next year. But that is just a limitation right now when we do offshore turbines. I'll stop there. Yeah, ask if there's any questions on the offshore capability. Okay. Community, I think Amanda went through this. I'm not sure I need to go. I'll just go quickly. Everything OpenFAST, of course, developed on GitHub. So use that for source code control. And again, you can download executables if you're on Windows. If you're on Linux or Mac, there's a quick conda install for you that will do all the download and compile for you. Yeah, if you have questions on the source code or theory of OpenFAST, or you have some new feature or bug you want to report, definitely use the GitHub repository for that. And if you're going to be contributing code, of course, this is your first place to be to access all the source code. Documentation on read the docs, again, always, before you have to ask a question, always check the documentation first. Again, it's keyword searchable, so you can type in that variable name as Emmanuel showed you. You can find it there. For more general usage questions, again, we have the forum. First step to use the forum is you create an account, and there's a process there outlined. Some people still have trouble with that, but yeah, as we said as well, we don't have a large budget to do this, so there's a lot of just free time supporting it, but we think it's important for the community. But yeah, also, if you have a question, most likely, we've had this forum active for 20 years now, so most likely your question's been asked before. So search first and then ask later. I just encourage that. We have a lot of other tools that are a bit more old. Like I don't think like MLife or MXtremes we've touched in years, and so we have basically an archive of the old tools here. So if you ever need something like that, or an older version of FAST, you can find it on this Wind Data Tools site. People always ask about who's actually using it. And we have a hard time tracking this now after we switched to GitHub. yeah, our last estimate was probably around 10,000 users of OpenFAST around the community. So consider yourself lucky that you're here. I guess you're one of 10,000 users around the world, over across about 4,000 institutions. And a lot of, obviously, I think we dominate the sort of research marketplace in terms of usage, but we also have quite a few industry users as well. And so for the industry users, I would say there's 5 levels. Our per level is level 1, where, people come to NREL and they say, well, we want to do something else. You can do this, but we want to add this feature, or we want to validate that. And so we actually have a lot of collaborations directly with industry supporting them on the tool. Not very useful if you're a student, but at least if you're going to industry, you should be aware of that. There's a lot of other industries that sort of, aren't working with us directly, but they're, it's open source. So they take it, they modify it, maybe they use part of it in their own tool. Yeah, and a lot of people are also just using it to check against, because we're the big open source version. Yes, and again, as I mentioned, open source, it's meant to be a two-way interaction. So we're also getting more and more over time contributions from the external community back into the fork. But again, if you're doing that, if your goal for your PhD or postdoc is to improve OpenFAST in some way, I think, as Emmanuel said, reach out to us sooner than later is always better, so we can point you in the right direction. Any questions on that? That's probably straightforward. Okay. Source code. You don't need to source code if you're not going to change it. Maybe it's useful if you want to check something, what's some detail of something, you can always go to the source code. But it's good to, because we have a very modular architecture. I think last time I asked, I think there's 2 million lines of code these days? Maybe it's up to 4 million. So it's huge. So finding what you need, sounds like it'd be a nightmare, but it's actually very systematic. And so that's what I want to lay out here as a sort of system. And so first of all, when you understand the source code, you really have to understand data structures of how the data is stored in the code. And so I showed these images on the top before. So you have, a module has inputs, outputs, states, and parameters. And all the variables are clearly identified as such in the code. So all the states basically are this what we call Fortran type. So every continuous state has an X parenthesis. X% sign is a continuous state in the model. Discrete states are XD, constraints are Z. Other states are things like binary states or something. Also, inputs are U percentage, outputs are Y percentage. So you can clearly see this in the code. Like if it has one of these percentage symbols in it, it's definitely one of these variables. Parameters are stored as P. There's a few other things you'll see. There's what's called a MISC var. That's usually it's something that is used for. It's mostly like a local. It should be like a local variable, but maybe it's a big array that we don't want to allocate every time step, and so we store it as a MISC var. It's basically a way to make it more efficient. And if it doesn't have any of these percentage symbols in front, it's really a local variable, so only used by that subroutine. To make all these data structures manageable and consistent across all the code, we have what's called this registry of OpenFAST. And so all these variables, whether it's an input, output, state, parameter, get set in what's called the registry.txt file. So every module will have one of these registry text files that will basically define what all its inputs, outputs, states, and parameters are. And so if you're curious what an input or an output of a given module is, or what its states are, quickly go to the registry file. It will lay that out for you. What the registry does is it's actually an executable. It's actually a C code that takes that text file and automates source code for it. So it'll generate these basically 4 sets of routines in this what's called types file. And so the key with these types files is you never change them. Never locally change them. If you ever want to change what's in a types file, you run the registry again. That will do that for you. But because we're doing a lot of sort of systematic things in our solve, like we have to interpolate or extrapolate inputs. Again, we just define what the input is, and then this registry will automatically generate that interpret extract routine. Same thing for pack unpack. That's useful for the save retrieve capability or checkpoint restart. Copy destroy, that's for the types. So all these sort of basic data handling routines are automatically generated for you. Also, every module looks the same in terms of its core subroutines that, say, the glue code will end up calling. There's really 4 main routines that you'll see in every single module. One is the init module. So one is the init routine that basically initializes the module. So that's where the parameters get defined. So whatever constants of the model, that's where they get set. That's where it initialize the states of the model. Another similar routine is called the end routine. That basically closes out that module. So all of the data of the module will be deallocated. If there's a file that it needs to generate, it will finalize it and write it in that routine there. And then showing again the data flow through those modules. Those the init and the end. So that's the start and the end of the simulation. The 2 main time domain subroutines you'll find again in every single module of OpenFAST. One is the update states routine. That basically says, so given the data that I need at time step n, advance that to the next time step n+1. So you see the states are coming in there, the inputs are going in there at n, and then that basically outputs the values at n+1. I should say that the states are coming in at n, or t going to t plus t, but the inputs are actually an array, and that's because some of these modules require, if it's an explicit module, it would say, well, I only need to know the data at n to get to n+1. I don't need future information. If you have some sort of implicit module, like a generalized alpha routine or a Runge Kutta routine, it needs to know inputs in the future to get there. And so that's why we sent an array of inputs. So that basically stores this extrapolation history that allows that module to access that data to advance its states. Let's see. So the calc output routine is the other one that we'll call every single time step. And that basically says, it's an algebraic solve. So given everything at the current time step, give me that output y at that time step. So again, you can really now hopefully picture, all these millions of lines of code. Hopefully you can see it now. What's initialization? What's an update state? What's an output solve? And that's how we always think about it in OpenFAST. There's a few other routines that you'll see that may or may not be there depending on the module, but these are, one is a calculate continuous state derivative. So if you remember when I talked about earlier, that's that big, x in my differential equation. Calculate continuous state derivative returns that big value of x. So that's basically the state derivatives at that set of inputs. Update discrete state, it's discrete states at n and allows them to go to n+1. Calculate continuous state residual, basically calculates the residual function, what we call z in the solve. Again, it's an algebraic setup. We also have 4 other routines that may or may not be in a module. These are all the ones that calculate the Jacobians that are needed for linearization. And these you'll also see, again, some of these are fully analytical formulations of Jacobians, some of them are finite differences, but you'll see that in the code as well. So anyways, every module will have at least 4 of those routines. So some of them have all of them. But all the calculations are basically split out in those routines. They may have other, local subroutines that these modules will call to do some work, but at least they're all structured that same way. So that, anyways, that hopefully gives you a sense of this big code and how it's structured out. So data and then the subroutines. Any questions on that? Hopefully that's useful if you want to get in the code. Nothing? Late in the day, I guess. So this this I'll just kind of go through some. Again, this is mostly if you already use OpenFAST, you know, what's sort of coming, what's sort of new and coming down. We've probably talked about some of these already. So yeah, Emmanuel presented this work at Torque, but in our 4.0 release of OpenFAST, we have this new new BEM solution that really works well at high skew angles. Before, we basically follow this say cubic loss. You know, if you have a yaw angle and you're 20 degrees off, we basically follow the cube, cosine cubed law before. Whereas when we compared that to CFD and Olaf, we showed, well, you know, the actual exponent was not cubic for a lot of things. And Emmanuel looked a lot at the theory basis and found this Glauert's skew correction method and got that into OpenFAST. And that really, relative to CFD, blade resolve CFD and actuator line simulations, gives us a much better answer for high skew angles. So before, we were always losing more power than we should have at high skew. So there's a nice Torque paper on that, and this will be in the 4.0 release. Tight coupling. I had a whole presentation on this last year at NAWEA, I think also at the Energy Science Conference last year, if you want to know all the details. But again, what we're talking about with tight coupling is taking at least a subset of the modules, in this case, BeamDyn, ElastiDyn, and SubDyn, and we tightly couple them with one common solver, and that's done through a generalized alpha approach. You can see in this slide, there's 20 modules of OpenFAST that we have. Which ones are loosely coupled here in 5.0? Which ones are now tightly coupled? This also clarifies which ones have explicit and implicit type of coupling. So all the explicit modules that are loose basically get staggered in series. You know, we just serially connect them together. Everything tight gets up in a big generalized alpha solve, and everything in the implicit basically gets shown up in one big Jacobian that we ensure is consistent every time step. And so the details are in a paper that's coming out. I know these results are slightly outdated. Last I saw from Derek on Friday, there wasn't a yellowed out area. So all the cases were now running. There was just a bug in this version from a few months ago. But before, again, we're BeamDyn. I think for this case of the IA 15 megawatt with the 10 node BeamDyn fine element model, used to take 20 hours to run. Now it takes 20 minutes. So it's a huge change. So it depends on the model, but we're seeing 10 to 100 times faster than it was before. So I'm super excited to see this coming out in 5.0. You can see some results there as a function of different time steps. You know, we don't, for the main frequency range of interest, has no effect. The big thing it's doing here allows us to take much bigger time steps than we could before. So again, that should be available by hopefully the end of December. So I've been promised. If you're into multi-rotor systems, actually I have a whole presentation on this at NAWEA coming up on Wednesday, I think. And so just give you a quick snapshot though, a lot of, we have a very modular code, and HydroDyn already supports multiple rotors through Olaf. And so this was just a matter of taking OpenFAST and now dynamically allocating multiple instances of ElastiDyn, multiple instances of SubDyn, and coupling them to the same subset of SubDyn and HydroDyn. And so, yeah, this allows us to do, either multiple rotors in the same support structure, same tower, or like a multi-rotor system on a given floater. So super excited to see this coming out. It'll be released in 5.0. AC/DC, super excited about that. And I think you already showed how to use it, so that's great. I know Campbell diagram generation, if you were using OpenFAST a year ago, like this, anyone could do it, but it was work. And it took some skill and knowledge about how to do it. AC/DC really automates that whole process, I would say. So that's great. Wise, I would say this is a bit more advanced than we can do today, but really that says, well, OpenFAST is great, but I need to do a lot of scripting to run lots of cases. And I also usually want to do it, not just, analyzing a given turbine, but I want to optimize that turbine. I'm going to redesign the blades, redesign the controller, whatever it is. I'm going to do it in some iterative optimization loop. And that's what WISE is set up to do. So it really is serving two purposes. One is our load case generator to run all the cases that you need, say for IEC or some parametric sweep. But it also has a feedback loop where you can optimize it on things. Throw constraints in there, throw an objective function in there. It doesn't have to be just physical things like mass or power or something. You can have those, but you can also put cost models. So we also bring in all the cost models in here. So Wisdom has a bunch of cost models. Some are like sizing type models, some scale with mass, some are more, built up based on the components of the system. WISE is also multi-fidelity. So usually we say OpenFAST sits at the highest fidelity of WISE. And running nonlinear time domain installation space at high fidelity end of WISE. To make a lot of WISE run faster, we do a linearization of OpenFAST and run basically linear models through. So that makes the loads analysis process much quicker in the linearized time domain. Obviously less accurate. It's still only good for the operating point that you linearized about. And then we also have a frequency domain model called RAFT, really useful for floating wind, doing like REO calculations. And so when you run WISE, you can choose what levels of fidelity you want in there and base your optimization at different levels of fidelity. So a lot of work has been going on onto this to make it much more user-friendly. And we are promising next year, for those interested, we're going to have a workshop dedicated to this platform. Just a quick summary of some V&V we've been doing. I think V&V is obviously critical. So there's papers and all these things. So Emmanuel and I and Mayank have been involved in task 29 and 47 that uses Dan Arrow turbine in Denmark, heavily instrumented inflow and structural response used to validate the elastic capability. I think more recently, I think you'll probably see quite a few talks this week on RAW. But the nice thing about RAW relative to Dan Arrow is that in addition to all the inflow, now the inflow is much more highly characterized than we had before with spinning LiDARs and radars and vertical profiling LiDARs and so on. But in addition to that, we also have LiDARs looking backwards to track the wake and really trying to do not just stochastic validation, but also time resolved validation. So there'll be quite a series of talks on that this week. I think Ken Brown and a few of us wrote a paper showing some time series, some stochastic validation of OpenFAST. For the offshore interest, we had a nice partnership with Polimi, who's here in the room, but running, you're from Brentwood, sorry about that. Your colleagues at Polimi did this great experiment where they, surged and pitched the turbine in the wind tunnel. We used that to validate aerodynamic motion under large, surge and pitch motion. And then also looked at things like the floating tetraspar and validated our capability to do that. In the Atlantis project, we were looking at different ways to actuate, add damping, like 2 mass dampers or something to the floater. And we had experimental tests with, say, TMDs in the floater, and we were able to validate that capability as well. In terms of some recent applications we've been focused on, this is just really NREL now, but a lot of work on different floater types. I think we're quite unique in the marketplace and being able to do all sorts of different floaters. Different semis, TLPs, hanging ballast systems, different actuated devices. The T Omega Wind is a great example. You'll probably see this week, I imagine. And so, just a variety of loads analysis of different types of floater designs we've been looking at. Here all week, I'll be presenting Friday on our recent work to do sensitivity analysis, basically trying to say of all the thousands of inputs that Emmanuel showed in the input file, how do we figure out which ones of those really matter for the output? So we've done a series of case studies on that, and I'll present our latest one on Friday showing parked idling cases. What's most sensitive for parked, storm type cases? I think, quite interesting to see. I think the Wintery science paper was just released a couple weeks ago, so you can see it if you want the preview, but I'll present on Friday on that. And then Emmanuel led this effort. I think another unique application of OpenFAST. It's not just doing, you know, time domain loads analysis, but also using OpenFAST now basically as a digital twin. Basically use OpenFAST as a digital virtual sensor in conjunction with a real prototype. So in this case, we're basically trying to take measurements off the real asset, in this case, the TetraSpar prototype, and saying, can I use the measurements? I am doing just a few measurements like the SCADA system and IMU. From that, we reconstruct the full state of the OpenFAST model. And then once you know that, you can output anything OpenFAST knows. And there's a nice paper on that showing the validation for tower links. Definitely see a lot more work in that space going in the future. Yeah. Anyways, that's hopefully a quick snapshot of kind of some of the things going on. Again, you'll see a lot more this week in NAWEA that gives you a sense of what we're doing. Any questions on any of that? Okay, I understand it's late. No worries. Last section is just my outlook. I guess trying to look forward to where I see. So a lot of you guys are PhD students, postdocs, maybe going to industry soon. Here's where I see this stuff going. And so hopefully paint a little vision for that, and also maybe spur some ideas for you guys to work on. Please. Yeah.
There are multiple there. For the weight and different. Think about it. It makes sense to use fast farm in a confined environment like something we have been reflecting on quite a bit.
So this is a multiple turbines then in the wind tunnel, or?
Single turbine and then two in a row. But my concern was, is it meaningful
right
to use fast farm where you have a lot of blockage and basically we have like solid works around.
Yeah. Well, maybe we didn't really talk too much about fast farm today. I'll first of all say that there's a difference between near wake and far wake. Where I say like the near wake, the vorticity is really important. Vorticity starts breaking down, then eventually you get basically a Gaussian shape right of the wake. So for that sort of near wake part, we just say that's maybe 2 to 4D depending on turbulence level or something. So that for that near wake, like Olaf that's what you want. In that far wake where it's this is sort of broken down, now it's just a bunch of mess and it averages out some Gaussian shape. That's what fast farm does well. It captures that far wake, perfect for that. What's the higher level of turbulence? What's this deficit the next turbine's going to feel? So that's what fast farm is for. If you're talking about the blockage of the tunnel itself, because you're confined the flow, to me this is probably well, the first thing is the inflow generation. So TurpSim probably wouldn't be the appropriate solution. Probably what you really want to do is some large eddy simulation of that. What's the block of the wind? Right. And so what fast farm does is the whole wake is based on the inflow. So if the inflow has turbulent structures in it, the wake of fast farm will meander with that structure. So if the blockage is like really high when you're like influencing the expansion of the wake, then yeah, fast farm would be good. As long as you're not worried about wake expansion blockage level, then I think it would be appropriate. I think fast farm though is also like it's good for turbulent flow. If it's like purely uniform inflow, I'm not sure fast farm gives you much benefit, I guess, because it's really about the meandering wake out of turbulence part. So does that help? I maybe it's an Olaf problem. 3D, yeah.
Distance where you're not really in the far wake yet.
Yeah. 3D is pretty close. Again, the Olaf may be the better model again for this one. Yep. Yeah, see that, I mean, 3D is like right at the boundary of like, maybe it's good. It probably depends on how turbulent the inflow is. If it's like fully uniform, I imagine you're in the near wake. So OLAF would be the better model. But if you're throwing all these like, turbulence generators or something, fast form might be good. Great question. Okay, outlook again, vision where I see going forward. If that's useful for anyone. You think of like, these are sort of the main themes, I guess. No details here, but these are the main themes that I would say we focus on. One is V and V. Like I want to understand all these models that we have, where they're valid, where they're not, where do we need to improve them in the future. And so a lot of our work is on using high fidelity models or measurement data to validate and make sure we have that sort of reason of certainty around where our models work and where they don't. A lot of papers on that topic. Wherever we find gaps in that, this physics model is not doing what we expect it to, or we could do better, do a lot of work on improving physics. Like the example I mentioned with the manual, fixing our skewed wake model for high yaw angle. Also, new technology coming down the pipeline. I have some new, LiDAR sensor that's going to measure inflow with that. That's in OpenFAST now, but yeah, some new technology that's not physically in there. So that we'd want to add. Again, a lot of our work is on understanding what drives the design in terms of all the inputs that we have in OpenFAST. I'll talk about how we do that on Friday at the conference. So understanding design driving parameters, I think, is important. So what should I focus on? What should I get right? What should I measure right? Is an important thing. A lot of our work is on supporting not just users, but also developers. So again, if you guys have developments you want to make, we try to support that as a community. Definitely see a lot of AI ML buzzwords these days. And I see moving in that space in two ways. One is training surrogates from our models. I picture this a lot in the fast farm world, where maybe I don't want to run a full wind farm loads analysis all the time, but if I can develop a surrogate that gets the effect of my upstream turbines on my turbine, that's quite useful. The other area I definitely see is like some models of OpenFAST. Definitely, we've had issues. You can tell, say, for unsteady arrow, I think we said there's 8 models now to choose from. That tells me like there's not one model that does it all. And so we're doing a lot of work on like saying high fidelity, CFD simulations of airfoils, and we just train a black box to give me that history system or something. So I definitely see that being more and more used in features, like replacing pieces of the model with an AI generated surrogate. See, of course, a lot of applications to design. In terms of areas that I think are high priority going forward, again, I'm curious if you have any different ones on these are sort of my not top 10, because I put more than 10 close. My sort of top list. And we're trying to get, we have projects in most of these areas and trying to build capability in these areas. But one is I've been trying to get funding for a while. I think we have some good leads now. How to get from global, so again, OpenFAST generates shear forces many moments out. But in the end of the day, same for my floater, I want stress strain each one of those, scantling the components of my floater. And so definitely a strong industry need there if you're doing detailed design of the structure. And so we have partnerships we're making to make sure that's a seamless coupling between OpenFAST and the FEA solvers. If you're in IEA Wind, task 56 has a huge focus right now on viscous hydrodynamics. So I think potential flow is great when potential flow is valid, but getting the drag coefficient right on different structures tends to be the hardest part of the hydrodynamic solve. Like what's my drag coefficient? And it depends on KC number and diameter and depth and all sorts of things, free surface, parts. And so you can't just say, well, I use one and it works for all. So we've been doing a lot of work trying to say, well, what's the approach that anyone would need to do to get a really good CD value? Usually it's some combination of some tank test or some CFD solutions, and we're trying to lay out a good roadmap for that. Steep and braking waves is sort of my next topic. I think we can do pretty good constrained waves now, but if they actually start rolling over and braking, there's definitely some nonlinear impact there that we don't capture well in OpenFAST yet. So a great topic. Floater motion induced aero. I would say we've done some validation there and we're pretty happy so far. But I think if, depending on the severity, amplitude, frequency, definitely some challenges if the motor motion's driving the rotor into stall or something. And so definitely I can see improvements there in the future. Let's see. As you know, we talked a lot about HydroDyn, so has, there's this unsteady airfoil part. There's also rotational augmentation models in there. And I'm quite curious how we should couple those things together. Can I just apply rotational augmentation, throw unsteady aero on that, or is there some deeper interaction there that we need to know about? High Reynolds number, definitely that's an issue as you get to larger and larger rotors, pushing Reynolds number of 20 million. Hard to do airfoil experiments, hard to do CFD. Stall, none of our X-foil wouldn't work at that high Reynolds number. So yeah, this is a challenge. Let's see, stolid vortex induced vibration. Again, a lot of what we do is for viscous effect is like, what's the average effect of drag, but we don't actually track the vorticities being shed from drag. This can be really important, say, for the tower in a storm condition. Standstill blade vibration, also deep stall, the drag, definitely an area where more CFD needs to be done and good engineering models derive from that. Complex terrain, definitely a challenging problem, mostly on the inflow side, but likely some impact on how wakes meander and so on. Air sea interaction, mentioned that one already. Right now, we based two independent stochastic processes. I think that's we use that all the time for design, but curious how much the waves will impact the wind and vice versa in the microscale. So I'd love to understand that more. Atmospheric stability. So all the IEC standards are based on neutral conditions, and we know in reality that they're stable and unstable conditions, and these have a big impact on wind farm performance. And so including that into the design process is quite important. Tropical cyclones, if you're not at this meeting, you're probably at the 10 this week. I'll be there 10 tomorrow talking about impact of hurricane events or tropical cyclones on wind turbines, a big design challenge, US, Gulf of Mexico, or Southern Atlantic or something. Blockage and deep array effects. Our fast farm models, I would say, great for tens of turbines, but if you get to hundreds of turbines, there's definitely different physical effects. The wind farm will disturb flow and create blockage. There'll be a big boundary layer that forms over the farm and affect deep array. There's gravity waves, of course, in there. And we are starting to develop some models in fast farm for those things, but definitely more work in the future there. And then cluster waves, the impact of one wind farm on the other, definitely something we don't have a good engineering model here. Slide. Yeah, so I think hopefully we've made it clear that these models are useful, for innovating design, optimizing systems, doing reliability, making rotors cost effective. And as you look to larger rotors or novel controls or coupling to offshore, design at the plant level, like these are extremely important tools. Yeah, I love this quote from Professor Box. I think he's now passed now, but he said essentially all models are wrong, but some are useful, and I think we definitely fit that mold very well. We know there's assumptions that are not always valid here in these models, but yeah, they're useful, they're important. So thanks for taking the time looking at them today. Yeah. So that's it. Any questions on that sort of vision direction? Yeah, happy to take questions.
What's the next target size? How do you say the thing? Think models around larger than that. What are they?
Great question. Well, your crystal ball is as good as mine, but because 20 years ago I would have said 5 megawatts is you're not going to go beyond that. That's crazy. That's crazy talk. So I was definitely wrong about that. yeah, I mean, I think the industry is sort of at that stage where like, whoa. This is crazy because it takes if you're kind of going from 100-meter blade, 150-meter blade, like that's a new factory now. I can't just extend my factory, so that's a 10-year development effort. So I think the industry is growing too fast, and they're suffering from that. And so the industry said, well, can we slow down? Like, let's stop at say 15. Let's optimize that. Let's build up supply chain. Let's make that real and cost effective. I think, yeah, there's definitely it is a market. So if it was one company, they would have done that a long time ago. But okay, maybe Vestas wants to stop, but some Chinese company pushes it further. So I don't know. I think that's definitely, yeah. So I don't have a crystal ball there. I mean, I definitely see this square cube law eventually, but like I think we've gotten bigger because we've been able to keep the mass from following the cubic relationship, drop innovation, but eventually we're probably going to hit the limit and it's going to be a square cube law again. And then at that point, I don't think it makes sense to keep getting bigger. So multi-rotor concepts, I think definitely we're interested in that case. Yeah, I'll talk a bit about that on Wednesday as well if you want to come to my talk. But yeah, I don't know. That's my take. So I mean, land-based, I think 5 megawatts. I just can't see transportation-wise. It's probably going to settle out there. Offshore, that's where this limit is. I have no idea, but I expect it won't be 30, 50 megawatts. I think it's going to go more to multi-rotors at that point. So, but I could be wrong. Don't quote me. Great question, though. Others? Yep.
Is there any effort at the power clockwise motion vibration? Is that something you guys?
Yeah, so via the tower, definitely it's on our. I mentioned it as a need. I would say I think it's really important for a couple of conditions. One is of course the installation of the tower before you put the rotor on, or keep a lot of damping from the rotor. The VIV can be quite important. Also some standstill parked storm cases that can be important. We simply haven't been funded yet to develop models. There's some nice models out there, not just CFD. Of course, CFD can do it, but just some good engineering models as well that can do that. We'd love to get those in OpenFAST at some point. So yeah, I think I saw some great ones at Torque actually on that topic. So definitely see that as a need. Anyone else? Well, again, I would say thanks a lot for being here today. We're ended early, so there's time if people want to stay and talk. Again, there's a evaluation form on that tiny URL link, so please send us feedback if you want something different for next time around. Just want to say something good too. Otherwise, yeah, no, thanks a lot. We'll see you around this week. Office hour on Friday, 1 o'clock. If you didn't sign up, don't worry, just show up. It's fine. It is going to be from 1 to 2 on Friday. Emmanuel and I will be there, maybe others from the OpenFAST team. And there's a room. It's in the program. It's in the program. And if you signed up for it, you should have got it's on the side event page. Like you can find it there. It's just an office hour. So nothing planned. But if you're doing your challenges that Emmanuel posed, you have time today or this week to work on it, come and ask those questions, or just have other challenges in OpenFAST, please see us then. Yep, that's completely open. No schedule there. So otherwise, yeah, enjoy your event this week, and we'll see you around.